Hello there, this is exercise 20b. It's our final look at projectiles in A-level maths. And we're looking today at trying to form some kind of general equation for the trajectory of a projectile. So that basically means a y equals x formula. Y equals x type formula anyway. So this is what it looks like. We obviously have, in this scenario, been given an initial velocity, and we're also told what the angle of projection is, and as we've seen, we can resolve those. We can resolve this so that ux is u cos theta and uy is u sine theta. And if you look at that, you basically write out the Suvat equation. You can do it in the x direction and you can do it in the y direction. And you quickly realize that if you ignore this v thing here, you could use the equation s equals ut plus half at squared. And in fact, you can do it in both directions. So if I put those things in, I get x equals u cos theta t plus half at squared. We've seen a few examples of the ax is always equal to 0. So that bit disappears in the x direction. So that's my final equation there. And then the y equation, I get this y equals u sine theta t minus a half. Now notice here I've written g. We saw an example of that again. Really, of course, it's minus 9.8, but we will write g for the sake of the equation here. So you get these two equations, and what we want to do is to try to solve these simultaneously. So let's do that now. I suppose the trick is to get the t. The t is always the thing that joins these two together. So I can write t equals x over u cos theta. That's quite easy to do. And then I substitute that into this equation here. I get y equals u sine theta times by the t, which I now know is x over u cos theta, minus a half g. And I've got this t squared, which is x squared over u squared cos theta squared. There. Now, can I tidy this up? Yes, of course I can. U divided by u is 1, so that disappears. And sine theta divided by cos theta, you should remember, is tan theta. So I can write this as tan theta x, or x tan theta. You can write that either way round, but basically it's tan theta times x. And this next bit, I can see I've got a gx squared on the top. Effectively, that 2's on the bottom of everything else, so I can write over the 2u squared cos squared theta. That may not look very nice, but it's actually the equation I wanted. This then, notice I've just switched those x and the tan theta around. This then is one version of the general equation of the trajectory. So let's have a look at this in action. A basketball player apparently is throwing a ball into the net, which is 3 meters horizontally and 1 meter vertically from the player's hands. So okay, so I've been given a lot of information. So from when he throws it to where it is going, you can see this is meant to be his hands. He throws it at an angle of 50 degrees, and we want to know how fast he throws it. We want to know the u. Let's just bear this in mind then, that later on it is 3 meters away horizontally and 1 meter up. It's at a height of 3, 1. If you like, that's my x, that's my y. So I can just substitute this into my equation. My equation says y equals x tan theta minus gx squared over 2u squared cos squared theta. And a lot of this information I now know. Y equals 1 equals 3 tan theta. Well, that's tan of 50. Minus g, well that's 9.8, times by, what's this, x squared is 3 squared, which is 9, over 2 times by u squared times by cos squared, that's cos of 50 squared. So effectively everything I know there apart from this u squared. So I can just type this in. I can say 1 equals, now 3 tan 50, I'm just going to do it on my calculator, 3 times tan of 50, make sure you're in degrees. I get 3.575, and I'm going to say 3 minus 9.8 times 9 divided by 2. 9.8 times 9 divided by 2. But then I also need to divide by that cos 50 squared. So I'm going to do that now, divided by the cos of 50. And I shall square that answer. And and I get 106, which is a huge number, isn't it? 106.734 divided by the u squared. So I'm just going to rearrange that. I get 106.734 over the u squared. That equals, well, that moves that way, effectively giving me 2.5753. These two switch places, which gives me 106.734 divided by 2.5753 must equal the u squared. Now that's u squared, of course, but divided by 2.5753, I get 41-ish. I was beginning to doubt that 106 figure, but I think it is broadly now reasonably accurate. U is the square root of that answer. And I get 6.44. 6.44 is it meters per second. That sounds a reasonable number. I'm not sure if it's right. 6.44, but here's an alternative to this formula though. And you'll notice I've got the formula on the bottom. I suppose I want to justify it to you. This is the formula which I just showed you. The problem with this formula is the fact that it says tan theta and cos theta. It's got both. So we try to get rid of it, and the way you get rid of it is you say y equals x tan theta minus the gx squared over 2u squared. Well, that's fine, but look, because 1 over cos is sec, I've got 1 over, effectively 1 over cos squared, so that's the equivalent of sec squared, so that's times by sec squared. And you'll notice that sec squared from what we've done in trigonometry is equal to 1 plus tan theta, tan squared theta. So all this disappears and becomes 1 plus tan squared theta. This is an alternative, and because it says tan and tan, this has advantages for us if we ever want to find what theta is. So here's an example, perhaps, of using this. A scientist measures the position of a projectile in flight. So he does it in 2 times, actually. It says when it goes through the point. Well, I'll do this one first. No, this one first. It's exactly 40 meters away. It is 20 high. And when it is 50 meters away, it is 10 meters high. So we've got these 2 coordinates. 40, 20, and then 50, 10. And I can put these y and x values into this equation, and it should give me enough information to find u and theta, I think. So it says form a pair of equations and solve them simultaneously. Okay, let's go for this. If I put y in, the first one will give me 20 equals 40 tan theta. Now I've got to do a bit of work on this. So this is g, which is obviously 9.8. So minus 9.8 times 40 squared divided by 2u squared, and it's 1 plus tan squared theta. And if I put it into the other one, what's this? This is equal to 10 equals 50 tan theta minus 9.8 times 50 squared over 2u squared, 1 plus tan squared theta. Okay, I'll transfer that on to the next slide. So this then equals 20 is 40 tan theta. I can type in a lot of these sums, so I'm going to do it now. I've got 9.8 times 40 squared divided by 2, and that's 7840 over the u squared still, 1 plus tan squared theta. And on this one I get 10 equals 50 tan theta minus 9.8 times by 50 squared divided by 2. 1250 over u squared, 1 plus tan squared theta. And you'll notice it's not very nice, but I could, if I wanted to, get an expression for u squared in both situations. So I'm going to rearrange it. That moves over there, that moves there. I've got 7840 over u squared 1 plus tan squared theta equals 40 tan theta minus the 20. And if I switch those round, I get 7840, 1 plus tan squared theta divided by 40 tan theta minus 20, and that's equal to u squared. So I've just switched those two bits around. I can do the same thing over here, and it will give me 12250, 1 plus tan squared. I'm just doing exactly the same thing, and divided by 50 tan theta minus 10 equals u squared. And because they're both equal u squared, that equals this. So therefore I get an equation that says 7840, 1 plus tan squared theta over 50 tan theta minus 10 equals, oh, I've mixed those up, terribly wrong, for 20, equals 12250, 1 plus tan squared theta over 50 tan theta minus 10. Now notice they've both got this term here, so they both cancel, and that's made my life a lot easier. I can move this up here, I can move this up here. I've got 7840 times by 50 tan theta minus 10 is equal to 12250 times by the 40 tan theta minus 20. So I'm going to multiply out those brackets and collect all the tan thetas on one side. So that's 50 lots of the 7840, and I'm going to subtract from that minus the 12250 times by 40. And that gives me minus, moving all the tan thetas on this side, I get minus 98,000, ridiculous numbers here, tan theta. And I'm now going to move this thing and this thing and expand it, but then move those numbers onto the right. So I'm going to do 12250 times by 20, that's the negative version of that. I get minus 245,000, and now I'm going to add on to it the 7840 times by the 10. And I get minus 166600. So I can ignore the minuses on both sides. Tan theta is 1 divided by the other. So I'm now typing in my calculator 17 over 10, and therefore theta is the inverse of that, inverse tan of the answer. I get 59.5 degrees. So it just goes to show you can work this out, and presumably I could put that 59.5 into this equation to get what u squared is, and then get u. I'm running out a bit of time. Do I get 59.5 worked? And just try that. See if you get 25.2 when you put that 59.5 in. I'll just mention a couple of things before we go on. There is an alternative to this again, and it's to leave it as x squared. So I left it as sec squared just now, but then I've also rewritten it as tan squared because I said I prefer it, and I saw this on an exam question. We're not going to do it now. I shall give you the answers to it, but you should by now really be able to do this. This was something that came up in the exam question, and I think it could come up in your exam where they actually ask you to prove that this is a formula. They could equally ask you to do one of the two other ones. Remember, this sec squared could be written as a tan squared theta plus 1 instead, or it could be written as a cos squared theta on the bottom as well. So all these variations could be asked of you in the exam. And then after that, it basically wanted, with decimals, it wanted us to find this equation and then to answer it to find the time of flight of the shot. So that was quite a tricky question, which theoretically could come your way. Here are the answers, by the way, if you go down that route. See if you can try and do that, and if need be, we can have a look at that in class. And in class, we'll do exercise 20b. This is all to do with this formula, but remember there are 3 different versions of this formula as well, so we could be using any of the 3, whichever one we prefer, whichever one we think works best. So exercise 20b, page 460. Okay, thank you.